Hey, what's up, everybody? Welcome back to another riveting episode of BC Calc Material. Today, we're going to talk about intervals of convergence. That's right. On the heels of Taylor and Maclaurin polynomials and on the heels of series convergence, we're going to talk today about how to show the length of x values that certain power series converge on. All right, more on that here in a second. So what do we need? We need a healthy respect for infinity. We're going to use the ratio test today, if you remember that good time. If you don't, click over here to see the ratio test video, and then come back and figure out how to do intervals of convergence. So then we need also to solve in absolute value inequalities, that old treasure from algebra. All right, so the old geometry nugget, right? All squares are rectangles, but not all rectangles are squares. That old nugget, right? So the Venn diagram of polynomials here, we would have squares as are rectangles, and rectangles are part of a bigger group of shapes called parallelograms. But parallelograms are just part of a bigger group of shapes called quadrilaterals, and quadrilaterals are even part of a bigger group of polygons, and so we get this nested Venn diagram. Well, that's kind of how it works for Taylor and Maclaurin polynomials as well. So here's a nugget from calculus. All Maclaurin polynomials are Taylor polynomials, but not all Taylor polynomials are Maclaurin polynomials. Okay, that doesn't have the same ring as the square rectangle thing, but it still is true. So we have another Venn diagram that we can look at here for Taylor polynomials, etc. So now, Maclaurin polynomials are the type of Taylor polynomials that are centered at 0. But Taylor polynomials are part of a bigger set of series known as a power series. Now, a power series is basically a series that has x raised to a power. Wonder where it got its name. Yeah, it's just x raised to power. Here's what it is. So a power series is just an infinite series involving powers of x. So that would be the sum from n equals 1 or 0 to infinity of some sequence of coefficients a sub n multiplied by x minus c raised to the n. And that should look kind of familiar because c is still referenced as the center, and then a sub n is a pattern of coefficients. Now, if we replace a sub n with this, the nth derivative at c divided by n factorial, yeah, you get a Taylor polynomial. Okay, so if specifically we have a function f and we can keep taking derivatives and evaluating at some center value and dividing by n factorial, we get a Taylor polynomial. Make c 0 and you get a Maclaurin polynomial. So you see how these are structured. Power series is all of them, Taylor series, and then inside of that we've got Maclaurin polynomials. Now, what we got to remember is that this is still an infinite series. Check that, that's an infinite series. So we talked about when infinite series converge. We talked about tests like the nth term test and the ratio test and comparison tests and alternating series tests. There's all kinds of tests to show that a certain series converges. So sometimes with these power series, some values of x will make the series converge, while other values of x will make the series diverge. So that's what I mean when I say an interval of convergence. We're wanting to know what values of x make this series converge. That's ultimately the goal. So power series are kind of a beast all unto themselves. So a power series may be the only way to represent a certain function. Now, what we did with Taylor polynomials is we took a function and we turned it into a polynomial. But sometimes these power series, what you see is what you get. The series is the only way to refer to a certain function, which is a little bit weird to think about, but some functions are just infinite series. Whew. It's a little bit odd. All right. So let's talk about the convergence of power series. So if these are functions, I just said that these power series are certain functions. Now, functions calls to mind domain and range. So the matter of domain, certain functions, right? The domain is all real numbers, but then there's other functions like 1 over 1 minus x, perhaps, and tangent x, where we have domain issues, right? 1 over 1 minus x, x can't be equal to 1. And then for tangent x, you can't have an odd pi over 2 because those are where the asymptotes are. So domain can be an issue. Now, the mystery surrounding these power series, sometimes you get a power series that only converges at the center. So that is when the value of the x minus c to a power, when that critter is 0, okay, you add a bunch of zeros, you're going to get 0. Sometimes you only converge as a power series at the center value, and that's it. Other times, though, around the center, you're going to get a interval around the center for convergent values. So we get like a little bit of a leash on either side of the center. And still others, you can converge for an infinite range around the center. So you converge for all real numbers. So these are the 3 different cases for the potential intervals of convergence. Only the center, a small window around the center, and then everywhere. Here, let me show you a picture. All right, so here is a picture for the different possibilities for the interval of convergence. So you see the only at the center case, a small radius around the center. The radius is important because it's the same distance on both sides. And you see in that case, that one's going to be a one we got to think about because there will be endpoints in that case. That's the only case where we have endpoints to think about, and we'll have to test those because we might include or we might not. And then you see the converge everywhere option. So it's almost like graphing inequalities, right? Where sometimes you had to include an endpoint or exclude if it was greater than or equal to or just greater than. You remember all that? Remember those days? Yeah, that would seem like a long time ago now. All right, so we're going to do the same kind of thing here with power series. So again, we're trying to determine the domain of the power series functions. What values of x make the infinite series converge? It's kind of a combination of series convergence tests and Taylor and Maclaurin polynomials. We're kind of blending those ideas together. All right, so the idea here is how do we find the radius of convergence? The radius of convergence for the first case would be the radius is 0. If we converge for a finite radius, well then the radius is a number, all right, for that case. Or if we converge everywhere for all real numbers, then the radius is infinite in size. So how do we figure out what the size of the radius is? Well, of course, it's the ratio test. Oh yeah, that old beauty. I love me some ratio test. And now if we recall the ratio test, remember we were trying to take a function, a series, and we were trying to determine whether it acted like a geometric series or not. Right, so that pseudo ratio, right, we took the limit as n went to infinity of the absolute value, the n plus 1th term divided by the nth term. As long as that pseudo ratio was less than 1, well then we had a convergent series on our hand. If the ratio was greater than 1, it diverged, and if the ratio was equal to 1, the ratio test was inconclusive. More on that in a second. Okay. So, I'm going to get you an easy one here. And I'll show you how we use the ratio test in a second while we work on this one. So, determine the interval of convergence for the series from 0 to infinity of x to the n. Now, hold on. Before you jump to the next example, just get yourself a simple one here. You might already know what's going on here. It's just a geometric series, right? Okay. Yeah, so what we want to know is, first of all, can we sniff out the center of this thing? Can we sniff out the center? That's x raised to the n. The center is, 0. The center is 0. So how far around 0 is this power series going to converge? Is it just at 0? Is it a small window around 0? Or are we going to converge for all x values? So here's how we find the radius of convergence. We apply the ratio test. So here we go. Limit as n goes to infinity, absolute value of the n plus 1th term divided by the nth term. Well, that's going to simplify to just the absolute value of x, and as n goes to infinity, we just get the absolute value of x. Now that is a little bit curious. We didn't get any of that scenario when we did the ratio test. We always got a number. So what does this mean? Well, remember, x is representative of a number. So for that result of a ratio test, we need that result to be less than 1 for the series to be convergent. So let's just make the claim that for this to converge, the absolute value of x has to be less than 1. So this calls to mind the solving absolute value inequalities from before. Remember I told you we were going to need that? So what values will work? Well, anything between -1 and +1, right? Everything in between -1 and +1, if you substitute into the absolute value of x, you get a number less than 1. So that means the interior of the interval of convergence is -1 to 1. So this is a case, that middle case, right, where we converge for a small window around the center. We can go 1 away from the center and get a convergent series. But what about the endpoints? What about the endpoints? Do we include those endpoints? Well, let's see. What's happening at the endpoints? Well, at -1 and +1, substitute that into the absolute value of x. Go ahead. Oh, wait. Yeah, you get 1. And what does that mean by the ratio test? That means nothing. That means we don't know that when we get the ratio test equal to 1, it's inconclusive. So what we need to do is at -1 and +1, we need to go back and see what the series becomes at those values. So when we substitute in -1, we get the alternating series, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. And we can do some funky stuff to that and to say that that converges to 1/2. That's a lie because that diverges. The nth term is 1, right? So this thing diverges, right? It diverges. The partial sums are either 1 or 0. They don't converge to a single value. All right, so we're not going to include -1 in the interval of convergence. Well, what happens at +1? At +1, the series x to the n becomes just 1. So 1 plus 1 plus 1 plus 1 plus 1, adoy, that's going to diverge. So can we include in the interval of convergence either of the endpoints? No, because at both of the endpoints, it resulted in a divergent series. That means the power series x to the n converges for the interval -1 to 1, non-inclusive. But we knew that was going to happen because that was just a geometric series that only converges, right, if the common ratio is, the absolute value of the common ratio is less than 1. We already knew that was going to happen, so that was why that one was a little bit easy, but we did it in a slightly different way. We involved the ratio test, we tested endpoints, the whole 9 yards. Let's look at another one. Keep going. All right, so here's another one, a little bit of a step up here. Determine the interval of convergence for this new power series. All right, x minus 2 to the n divided by n times 3 raised to the n. Now, if you're like me, you can probably sniff out the center of this power series real quick, right? So it was some pattern of coefficients and then x minus c to the n. You can probably sniff out, just like me, that the center of this power series is 2. All right, so we guaranteed that this thing is going to converge for at least x equals 2. But how much more? Can we converge for a window? Or are we going to converge everywhere? All right, all power series converge at their center, at least. All right. So we're going to conduct the ratio test. And I've already got it done here, but let me walk you through. All right, so we got the ratio test, the n plus 1th term divided by or multiplied by the reciprocal of the nth term. You see that right up in this little area that I'm highlighting. Check that out. All right, so then with some simplification, we can we can get rid of some of those pieces, right, and simplify. X minus 2 to the n plus 1 divided by x minus 2 to the n, that's just x minus 2. And then those 3 to the powers, that's just 3. So let's see what happens after all of the carnage. After all of the carnage, we end up with the limit is n going to infinity. You got n over n plus 1, that goes to 1. And then the rest of this piece just goes to the absolute value of x minus 2 over 3. Now, that again is kind of weird because we are supposed to get a number out of the ratio test, but we did, right? Because x is a number. And what we've got to show for the ratio test is that that result needs to be less than 1 to be convergent. So here we go. We're going to force that to be less than 1 and figure out what x values work for that absolute value inequality. So we can say that the absolute value of x minus 2 has to be less than 3. Now, I can solve that by doing like x minus 2 is less than 3, and or whatever it is, x minus 2 is greater than negative 3. Like I can do that part, but I can also interpret the difference, the absolute value of a difference as distance, okay? This is big, all right? This is going to make it go a little bit quicker if we interpret it correctly. Not just go through the motions, but use our mathematical interpretation to make it simpler, all right? So the absolute value, come back. The absolute value of a difference is distance. So the absolute value of a minus b is the distance between a and b. The absolute value of x is the distance between x and 0, right? That's how we kind of defined absolute value. So the absolute value of x minus 2 is the distance between x and 2. Now that is so important to see that interpretation because we've already pegged 2 as the center of this power series. So that means the distance from 2 that x can go is 3. So that means I can go 3 units on either side of 2 and be convergent. That gives me the interval of convergence to be -1 to 5. Now again, that's the interior, so that's not even talking about the endpoints yet. But I can move 3 away. The distance between x and 2 has to be less than 3. So everything within 3 units of 2, when subbed into the absolute value of x minus 2, will result in a value that converges via the ratio test. So now I've got to test those endpoints because at -1 and 5, both, you sub that into x minus 2 over 3, you get equal to 1 when you absolute value it. And that's inconclusive, which is why we need to test those 2 values back in the original series. So join me, will you? Here we go. At x equals -1, we've subbed that in to the original series, and we get -1 minus 2 to the n over n times 3 to the n. Well, that, after some simplification, is just the alternating harmonic, and we know that converges. So we're going to include -1 as part of the interval of convergence. Let's see what happens at 5. Sub 5 into the original series, and after some simplification, you just get 1 over n, the series. Now, that is the harmonic. It diverges. Remember? So we're going to exclude 5. 5, get out of here! We don't want you! So -1's in, 5 is out. So here's what we're going to say. The interval of convergence for that power series is -1 to 5, including -1, but excluding 5. Let's see another one. All right, here's this power series. I'm not going to say it out loud, but I think you can figure out what the center is, can't you? Yeah, I think you can. Did you find it? I knew you could. It's -4. All right. So we're going to apply the ratio test to figure out how far away from -4 we can go. Is it a certain distance? Is it a radius? Or is it just everywhere? All right, so ratio test. Hit it! So the n plus 1th term divided by the nth term multiplied by the reciprocal. We can get rid of all of that stuff. It's going to simplify down to the absolute value of x plus 4 over n plus 1. Now, I forgot to put the limit in there, but the limit as n goes to infinity for that thing is 0. What's that mean? What's that mean? What does that mean? Well, 0, last time I checked, is less than 1. That means for any x value you sub into that ratio test result, you're gonna get 0. That means every x value makes that series converge. So the size of the radius is infinity, which means the interval of convergence is all real numbers. Guess what? You can't test the endpoints because there aren't any. Isn't that fun? Let's keep going. Oh yeah, oh by the way, n factorial in the denominator. Yeah, if that happens again, probably gonna have some kind of all real numbers kind of thing. Not always. Always want to check. All right, I think this is the last example. Here we go. Determine the interval of convergence for this power series. Okay, what's the center? Yep, got it. It's pi. The center is pi, so I know for a fact this power series must converge at least pi. For a window around pi? For an infinite window around pi? I don't know. How do I figure it out? The ratio test. We're going to do it. All right, here's the ratio test in all its glory with the hayas included. So we're going to simplify all that algebra business, the factorials and the exponentials and the haya! We're going to get rid of it all, and we're going to simplify that ratio to m plus 1 times x minus pi over 2. And remember, n is going to infinity, so doesn't matter what x is. Doesn't matter, because that ratio goes to infinity. And the last time I checked, infinity is bigger than 1. That means it doesn't matter what x is. It's going to diverge. Unless x is pi. So how far around pi can we go? Nowhere. That means the interval of convergence, the size of the radius is 0, and the interval of convergence is that single center value x equals pi. There we go. So I think that's the last one. So we're gonna wrap it up here. So what have we learned? A power series, which is like the granddaddy of all series, like it includes Taylor and Maclaurin series. So there are 3 possible interval of convergence possibilities. Yeah, I said possibility a lot there. So it's only the center value. Only the center value. The radius would be 0 in that case. It could be a finite window of values, equidistant on both sides from the center value. So that is when the radius is a certain value. And then you could converge everywhere, all x values. So to determine the size of the radius of convergence, we are going to run the ratio test. The ratio test will result in this absolute value inequality. We need to make it less than 1. And then we can determine the endpoints of that interval. And then, oh, by the way, if you get endpoints, you need to test those endpoints back into the original series to see if it converges or diverges, because at the endpoints, the ratio test would have resulted in equal to 1, which is inconclusive. So if you get any endpoints, you have to test those values in the original series. All right, next time we're going to talk about error. And it kind of like alternating series error, but this one is going to be a little bit tougher. All right. Thanks for watching. Really appreciate it. Oh yeah, if you're not a subscriber already, click down here. If you need to watch the last video to kind of catch up here about easy ways to make Taylor polynomials, click over there so you can go watch that one. And I'll see you all next time. Thanks for watching. Peace. I said peace.